Hello students. Now I'll be taking up the last topic of the module 2, that is line integral of a complex function. As discussed earlier, any complex function f of z is given by u of xy plus iv of xy. Will be a complex function defined over region R and C is any curve in the region. Then the integral f of z dz will be given by u plus iv into dx plus I dy as z is given by x plus iy. So your dz will be equal to dx plus I dy. Thus integral f of z dz is equal to integral of the real terms plus I, the integral of the imaginary terms. In other words, the evaluation of the line integrals will be nothing but the evaluation of the real valued function. So to explain a line integral problem, I am just taking one example, that is evaluate the integral 2y plus x square dx plus 3x minus y dy over the limits 0, 3 to 2, 4. Along the paths, the two conditions are given. Parabola x is equal to 2t, y is equal to t square plus 3. Second path will be a straight line from 0, 3 to 2, 4. So for the first condition, parabola, I'll consider the limits same as 0, 3 to 2, 4. So the condition when x is 0, we can see clearly x varies from 0 to 2. So when x is 0, I get t as 0. And when x is 2, I get t is equal to 1. So when I change the variable from x to t will vary from 0 to 1. So substituting the values, y is given by t square plus 3 and x is given by 2t. So you'll have dx is equal to 2 dt, because all the variables should be in terms of t, and your dy is equal to 2t dt. Substituting these values and integrating as we do for real valued function and then putting the limits, I get the I is equal to 33 by 2 along the path parabola. Here, since the path is about the straight line from the point 0, 3 and 2, 4, I need to get an expression x in terms of y or y in terms of x. So I take the equation of a straight line passing through 2 points, which is given by y minus 3 upon x minus 0 is equal to 4 minus 3 upon 2 minus 0. From this I get x is equal to 2y minus 6 and also dx is equal to 2 dy. Since I am expressing all the terms in terms of y, I should consider the integral varies from y from 3 to 4. And substituting the values of the given equation and integrating, I get I is equal to 97 by 6 along the path straight line. So now let me take a very important theorem known as Cauchy's integral theorem. It says that if a function f of z is analytic through some simply connected region R for every closed path C in R, then the integral f of z dz is equal to 0. The other meaning of this theorem is when any given point, if that point lies outside the circle, then the function f of z, integral of the function f of z will be 0. And the proof for this is, let f of z is equal to u plus iv. Therefore, integral of f of z dz is equal to f of z is replaced by u plus iv and dz is replaced by dx plus I dy. Separating the real and imaginary parts, we have from Green's theorem, we had earlier studied that integral m dx plus n dy is equal to double integral r dou n upon dou x minus dou m upon dou y dx dy, where m of x comma y and n of x comma y are real valued function having continuous first order partial derivatives. Now applying the theorem for the above equation, I have integral f of z is equal to double integral r minus dou v upon dou x minus dou u upon dou y dx dy plus I double integral r dou u upon dou x minus dou v upon dou y dx dy. That is by we have that integral c m dx minus n dy is also given by minus of double integral r dou n upon dou x plus dou m upon dou y. And then since f of z is analytic, from CR equation I place dou u upon dou x by dou v upon dou y and dou v upon dou x by minus dou u upon dou x. On putting the CR equation, that is substituting CR equation and simplifying, I get integral f of z dz is equal to 0. Thus, the Cauchy's integral theorem, I stress on the word theorem, says that if any given point is outside the circle, then the integral of that analytical function is equal to 0. The next, once again a very important theorem called as Cauchy's integral formula. Please remember, the earlier theorem was Cauchy's integral theorem. Now this is Cauchy's integral formula. It says that if f of z is analytic inside and on a simple closed curve, and if A, now I stress the word if A is any point within C, then f of A is equal to 1 upon 2 pi I integral C f of z upon z minus A dz. Now as discussed earlier, if the point lies outside the circle, then you have to use integral theorem. And if the given point lies inside and on the circle, then you have to use the Cauchy's integral formula, which is given by f of a is equal to 1 by 2 pi I integral c f of z upon z minus a dz. Now proof follows as given below. Since A is a point within C, draw a circle C1 taking z is equal to A as center and radius r such that the circle C1 lies entirely within C. Now, since the function f of z was given as analytic, any term multiplied to f of z or divided to f of z also becomes analytic inside and on the boundary of the annular region between C and C1. From Cauchy's theorem, this is multi-connected Cauchy's theorem. We have integral C f of z upon z minus a dz is equal to integral C1 f of z upon z minus a dz. Now, C1 is a circle I know with center A and radius r. That is given by z minus a is equal to r e power I theta, or z is equal to a plus r e power I theta, and clearly since it's a circle, the theta value lies between 0 and 2 pi. And differentiating z, we have dz is equal to I r e power I theta d. Now substituting all these values in the above equation, I have integral c f of z upon z minus a dz is equal to integral theta from 0 to 2 pi f of a plus r e power I theta upon r e power I theta into I r e power I theta. After cancelling the common terms, I am left with integral 0 to 2 pi f of a plus r e power I theta d theta. Now here, for any value of r greater than 0, r tends to 0. Hence, the right hand side of the equation becomes I 0 to 2 pi f of a d theta. On integration and substitution, I get 2 pi I f of a. Further simplification leads to f of a is equal to 1 by 2 pi I integral c f of z upon z minus a dz. This is the result of the Cauchy's integral formula. Once again, I stress here, Cauchy's integral formula is exclusively used when the given point is inside and on the circle, and Cauchy's integral theorem is used when the given point is outside the circle.